In this example, we're integrating an expression that has sines and cosines in it. Now, we remember from a previous video that when you have an integral that has sines and cosines, the idea is to save either one sine or one cosine to use as the du at the end of your expression. And then we want to write the rest of the integrand in terms of the other guy, sine or cosine. And so basically our integral would wind up being a function of u with a du at the end. So you have some function of u with that one single remaining term, either sine or cosine, acting as the du at the end of the problem. Now, how do we decide who's who? How do we decide who we're going to save to be the du and which function is going to be the u? Well, the idea was to save the term who has the odd power, and we'll talk about why that's the case. So this guy has an odd power cosine to the fifth. So the odd power is going to be the term that is saved at the end of the integrand. So we'll write cosine of theta d theta. And then our remaining integrand would be cosine to the fourth of theta divided by the square root of sine theta. Now here's why we save the guy who has the odd power. If you peel one term away from somebody with an odd power, obviously what's left is an even power. And if we have an even power, we can use trig identities to turn him into the other guy. For instance, we know that cosine squared theta, this is a basic trig identity, equals 1 minus sine squared theta. And so we can rewrite this guy in terms of sine. So everything in this pink box will eventually have only sines, right? Only sines. And then back here at the end, we'll have cosine, which will be the du. So we'll have a function of u, du. So let's see if we can jot down what this left-hand side would be. It would be the integral. Cosine to the fourth is actually this guy squared, because this 1 minus sine squared would need to be squared to be equal to cosine to the fourth. So we'd have 1 minus sine squared theta quantity squared divided by the square root of sine theta. And then we would have a cosine theta d theta at the end of the problem. All right, so a function of u with a du. So let's see if we can rewrite this now in terms of u. This will be the integral of 1 minus u squared quantity squared divided by the square root of u with a du at the end. And then from here, it's just a bunch of algebra. You can probably finish this out all by yourself, but I'll do it with you real quickly. We would FOIL the numerator. This would be 1 minus 2u squared plus u to the fourth divided by the square root of u, which I'll write that as u to the 1/2 power. It's the same thing. And then, so how are we going to integrate this guy now? Well, you'll notice you can break this apart into 1, 2, 3 separate integrals by dividing u to the 1/2 into these three terms. So we would get the integral of u to the negative 1/2. That's 1 over u to the 1/2 minus 2u to the, let's see, u squared over u to the 1/2. We'd subtract their exponents. 2 minus 1/2 is 3/2. That's 1.5 basically. Plus, then u to the fourth divided by u to the 1/2. That would be u to the 7/2. That's 8/2 minus 1/2 will make 7/2. And finally, we have something that's integrable. We can actually integrate this guy right here with relatively little trouble. Matter of fact, I'll just do it right up here in the corner. Maybe I'll change colors so it's not confusing with this guy here. Okay, so what will this integral be? Without going through all the detailed algebra, this would be 2u to the positive 1/2. This guy here would make minus, let's see here, minus, it would be u to the 5/2 with a 4/5 out front. That's 2 times 2/5. And then plus, let's see, this last part would be 2/9 u to the 9/2. And then obviously we'd have a plus c in here as well. All right, so the final answer, I don't know if I can squeeze all this in here together, but we would have 2. And then now we have to go back and figure out who the u was. Who was u? U was equal to, let's see here, if cosine was du, then u was equal to sine theta. And that's what made du equal cosine theta. So I'm going to take all the u's out and replace them with sines. So we'd have 2, basically square root of sine theta. We'd have minus 4/5 sine to the 5/2 of theta, plus, I'm kind of running out of space, so I'll wrap it around down here, 2/9 sine of 9/2 of theta plus c, right? So the algebra maybe wasn't the prettiest thing ever, but the process is identical to all of these other types of integrals. Just make sure you understand the general principle here. You have sines and you have cosines. You want to save one guy, put it in your pocket, save him. He's going to be the du, and whoever he is, in this case he was cosine, you want to turn everybody else into sines. Or if it was a different problem, if you had saved a sine in your pocket, you'd want to turn the rest of the integrand into cosines. And the underlying principle here is you have a function of u with a du at the end. You're trying to do a u substitution. So anyways, I hope this example helps you kind of wrap your mind a little bit better about that type of idea where we integrate certain expressions that have both sine and cosine.